Okay, let's continue our discussion of positivity in C-star algebras. So we already know what positive elements are. And now let's define positive functionals on C-star algebras. So suppose we have a star algebra, a star algebra, and a linear functional f on A. So the definition of a positive functional makes sense for any star algebra, not necessarily a C-star algebra. So we say that f is positive, and we use the following notation. If it satisfies the following condition, f of A star A is non-negative for every element in our algebra. Moreover, if we assume that if A is a Banach star algebra, and if we assume that f is bounded, then we say that f is a state of A, a state on A, if it is positive and if the norm of f is 1. In Russian, state is состояние. So the terminology came from physics. I'll tell you more about this in a few minutes. Okay, let's now observe that if A is a C-star algebra, then this definition can be written in the following way. If A is a C-star algebra, then a linear functional f on A is positive if and only if it takes, if and only if it preserves positivity. So if it takes the positive cone of A, the set of all positive elements, to non-negative numbers. Well, indeed, it follows from the fact that the positive elements of a C-star algebra are exactly the elements of this form. So this is true because an element B in A is positive if and only if it has the form A star A for some element A in our algebra. Well, the left-to-right implication is true because we can just take the square root. If B is positive, then we can let A equal the square root of B. And the opposite implication is true by Kaplansky's theorem, which was discussed at the previous lecture. Okay, let's now look at some examples of positive functionals. To begin with, let's observe that all star characters are positive. If chi is a star character, then chi is positive because it takes A star A to the absolute value of chi of A squared. And moreover, if moreover A is a C-star algebra, this is the case we're mostly interested in. If A is a C-star algebra and chi is a non-zero star character, then chi is a state on A. This follows from the fact that every non-zero star homomorphism between C-star algebras has norm 1. This was noted at the previous lecture. Example 2. Let's now take a commutative C-star algebra. That is the algebra C0 of x, the algebra of continuous and vanishing at infinity functions on a locally compact Hausdorff topological space X. In this case, the there is a one-to-one correspondence, there is a bijection between the set of all positive functionals on this algebra and finite positive Radon measures on X. So explicitly, if mu is a finite positive Radon measure, then the respective positive functional f mu is just the integral with respect to mu. It's rather obvious that this functional is indeed positive, and moreover, its norm is equal to the measure of x. This is a simple exercise. So in particular, we see that f mu is a state, even only if mu is a probability measure. And this bijection is actually a special case of the standard important result of the Riesz representation theorem. The Riesz representation theorem. There are several versions of the Riesz representation theorem. For example, if we replace here C0 of x by the algebra of compactly supported continuous functions, then positive functionals on this subalgebra are exactly positive Radon measures, which are not necessarily finite. But if we want functionals on C0 of x, then we must take only finite positive Radon measures. So since C0 of x is has any commutative C-star algebra is of this form, the general philosophy is that if A is an arbitrary C-star algebra, not necessarily commutative, then positive functionals on this algebra can be viewed as non-commutative analogs of positive Radon measures. Example 3, let's now look at the algebra of m by n complex matrices, or equivalently the algebra of linear operators on Cn. Here is a typical example of a state on this algebra. F of A is 1 over n times the trace of A. So this is a so-called normalized trace. So we divide the trace by the dimension of the space. And this is easily seen to be a state on A. Actually, it's rather easy to describe all states and all positive functionals on this algebra. To do it, let's call a standard result the so-called trace duality of this algebra with itself, which states that for every linear functional f on the matrix algebra, there is a unique linear operator, a unique matrix S in A, such that f is given by the following formula. This is the trace of the product Ts for every T. And let's denote this functional by Fs. So we get an isomorphism between A and the dual space A star. And then it's rather easy to see that this functional Fs is positive if and only if the operator S is positive. So here's a useful relation between positive elements and positive functionals. And moreover, Fs is a state if and only if S is positive and the trace of S is equal to 1. So example 1 becomes a special case of this more general construction. Okay, let's now take the algebra of bounded operators on an arbitrary Hilbert space. Example 4. So let E be the algebra B of H, where H is a Hilbert space. Let's take an arbitrary vector psi in H and define a linear functional f psi on A by the following formula. So this will be the inner product of T psi by psi. This functional is positive. So to see that it is positive, we simply apply it to T star T. We substitute here T star T. Then we move T star from here to here, and it becomes just T. And we see that this is the inner product of T psi by itself, which is non-negative. So this implies that f psi is a positive functional. Moreover, its norm can also be easily calculated, and it is equal to the norm of psi squared. This is a simple exercise. So we see that f psi is a state. F psi is a state, if and only if the norm of psi is 1. States of this form are called vector states on B of H. Well, now let me say a few words about where the terminology comes from. There are two fundamental notions in physics, observables and states. In the mathematical model of the classical mechanics, states are just points of a certain smooth manifold. That is the phase space of our mechanical system. And observables are just functions, real-valued functions on this manifold. The mathematical picture of quantum mechanics is different. Now states are vectors on the unit sphere of Hilbert space. That is, vectors satisfying this condition. And observables are unbounded self-adjoint operators on this space. And if T is an observable, if T is such an operator, then this number, given by this formula, is interpreted as the mean value of T, of the observable T, in state psi. States of this form are called pure states. There are also so-called mixed states, which are defined similarly to this example, to part 2 of example 3. So basically they are given by this formula. But now, since H is infinite dimensional, to make sense of this expression, we must assume that S is not an arbitrary operator. S is a so-called nuclear operator or a trace class operator. So in this case, we can generate a so-called mixed state. So if S is a rank 1 projection, then we come back to a vector state, to a pure state. Okay, let's now look at some basic properties of positive functionals. So we have the following theorem. Suppose that A is a C-star algebra and F is a positive linear functional on A. Then I claim that, first of all, it takes self-adjoint elements to real numbers. Second, F is Hermitian in the sense that it preserves the involution. It has the following property. And finally, F is automatically continuous. Well, just a few words about why this result is true. Property 1 is more or less clear because we know that every self-adjoint element is a difference of two positive elements. And F takes positive elements to positive numbers. Property 2 can easily be deduced from property 1. Actually, we have already discussed this in the case of characters. And for functionals, the proof is exactly the same. So if F takes self-adjoint elements to real numbers, then it preserves the involution. And to prove the continuity of f, we use some basic properties of the positive cone, of the set of all positive elements in a C-star algebra. So roughly by using some power series, we first prove that f is continuous, f is bounded on the intersection of the unit ball with the positive cone of A. And then using the fact that every element is a linear combination of 4 positive elements. So first we decompose it as a combination of 2 self-adjoint elements. And then every self-adjoint element is the difference of 2 positive elements. So as a result, every element of a C-star algebra is a combination of 4 positive elements. So now if, after we prove that f is bounded on the intersection of the unit ball with the positive cone, we deduce that f is bounded on the unit ball. So it is continuous. By the way, the same result is true for any Banach star algebra with a bounded approximate identity. But in this case, the proof is much more involved. Our next result gives several useful several positivity criteria for linear functional. And also it gives us a useful way of extending a positive functional defined on a C-star algebra to its unitization, which is rather useful. So let's introduce some notation. Suppose that A is a C-star algebra and f is a linear functional on A. Let's denote by f plus the following functional defined on the unitization of A and given by the following formula. It takes A plus lambda 1 to f of A. So initial choice would be plus lambda. But in the context of positive functionals, it would be more convenient to multiply this lambda by the norm of A, of f. Well, unfortunately, this notation is inconsistent with our earlier notation, which was introduced when we discussed star homomorphisms between algebras. But, well, I hope this will not lead to any problem. So when we deal with positive functionals, it would be more convenient to define f plus in this way. And the reason why it is convenient is included in the following theorem. So suppose that A is a C-star algebra, and let's take an approximate identity, E lambda, an approximate identity in A. Let's recall that when we speak of approximate identities in C-star algebras, we always assume by default that this approximate identity is positive. Its norm is bounded by 1, so in particular it is bounded, and it is monotone in the sense that if lambda is less than or equal to mu, then E lambda is less than or equal to E mu. So E lambda is an approximate identity, and suppose that f is a bounded linear functional on A. Then it turns out that the following conditions are equivalent. Condition 1, f is positive. Condition 2, the limit of the net f of E lambda exists and is equal to the norm of f. Condition 3, the norm of f plus, clearly f plus extends f. So condition 3 is that the norm of f plus is exactly the norm of f, which is quite convenient. So this explains in particular why I multiplied here lambda by the norm of f. And condition 4, f plus is positive. So we see in particular that if f was positive, then this functional f plus is also positive. So every positive functional defined on a C-star algebra can be extended to a positive functional on the unitization. So in a sense, this is a standard way of extending a positive functional. The proof is not entirely trivial. I can't explain it in a few words. This is a chain of several estimates involving some properties of positive functionals. Here's a useful special case, a corollary, useful special case of this criterion, which corresponds into a unital algebra. Suppose that A is a unital C-star algebra, and f is a linear functional on A. Then f is positive if and only if it takes the identity of A to the norm of f. Well, indeed, we just let E lambda equal 1 for all lambda, and we see that we get this condition. The condition 2 becomes this one. So this is equivalent to the positivity of f. Corollary 2 follows actually from corollary 1 and from this theorem. And it is very important because it gives us a way of extending a positive functional from a subalgebra to a bigger algebra. So suppose that A is a C-star algebra and B is a closed star subalgebra of A. I claim that in this case, for every positive linear functional G on B, there exists a positive norm-preserving extension. There exists a positive functional f on A such that f extends G and has the same norm. The norm of f is equal to the norm of G. The idea of proof of this result is rather easy. Indeed, we just take, first of all, we may assume from the very beginning that our algebras are unital and have a common identity, because if they are not, then we simply consider their unitizations and extend G to the unitization of B. So everything is reduced to the case where the algebras are unital. And in this case, we just take the usual Hahn-Banach extension of G. So there exists bounded linear functional f on A such that f extends G and has the same norm. This is the Hahn-Banach theorem. And now we apply corollary 1. Okay, so G is positive. So G satisfies this property, but f extends G and has the same norm. So therefore, f also has the same property. And now we see that f is also positive. So corollary 1 now implies that f is positive. And here is a useful special case, corollary 3. If A is a C-star algebra, then for every normal element, A in A, we can always find a state f on A such that we have the following equality. The absolute value of f of A is equal to the norm of A. Well, why is it so? The idea is very simple. We consider the C-star subalgebra of A generated by this element. This element is normal, so it generates a commutative C-star subalgebra. This subalgebra is just C0 of X by the Gelfand-Naimark theorem. And it's very easy to construct a state on C0 of X satisfying this condition. We just take a suitable evaluation character. A character is, of course, a positive functional and is a state. And then we simply extend it to the whole algebra by using corollary 2. And that's it. Okay. States are important for the theory of C-star algebras because for many reasons, but one of the main reasons is that they can be used to construct representations of C-star algebras. So let's now discuss the respective construction which produces representations out of positive functionals. This construction has a special name. It is called the GNS construction. GNS is for Gelfand, Naimark, and Siegel. So implicitly, this construction was introduced by Gelfand and Naimark in their first paper on sister algebras. And explicitly, it was introduced and investigated by Siegel a bit later. In fact, the theory of sister algebras is based on two fundamental constructions. So the first fundamental construction is the Gelfand transform, which we already know about. And the second construction is the GNS construction. So both constructions are very simple, but they are very useful at the same time. So we start again with a star algebra. A is a star algebra, and a positive functional on A. So the first step is to observe that every positive functional generates something like an inner product on our algebra. So more exactly, let's observe that the following formula defines a semi-inner product f of b star a. So if we take every pair of elements a and b to this number, then we get a semi-inner product. So what is a semi-inner product? This is something like an inner product that is a sesquilinear form. So it is linear in A and antilinear in B. It is Hermitian. So if we interchange A and B, then it will be replaced by the complex conjugate. And it is positive in the sense that the inner product of A by itself is non-negative. So the only difference between an inner product and a semi-inner product is that the semi-inner product of A by itself can be equal to 0. The fact that it is a semi-inner product is immediate from the positivity of F. So it is positive on the diagonal. In particular, it is real on the diagonal. And it's a simple exercise, algebraic manipulation, the so-called polarization identity, which implies that if a sesquilinear form is real on the diagonal, then it is actually Hermitian. So we get a semi-inner product. In particular, this semi-inner product satisfies the Cauchy-Bunyakovsky-Schwarz inequality, which can be written in the following form. This is the Cauchy-Bunyakovsky-Schwarz inequality. Well, the proof of this inequality for semi-inner products is exactly the same as in the case of inner products. Also, every semi-inner product generates a semi-norm on our algebra. So let's denote it like this. This is the square root of the semi-inner product of A by itself. So this is a semi-norm. On A. So to make it into semi-norm into a norm, we must quotient out the subspace where the semi-norm vanishes. So let's denote this subspace by NF. This is the set of all elements in A for which this semi-norm vanishes. And let's also observe, this will be useful, that we can just define this subspace in a slightly different way. Namely, NF consists of all elements A in A, such that F of BA is 0 for every B in A. This follows from the Cauchy-Bunyakovsky-Schwarz inequality. So if this is 0, if the semi-norm of A is 0, that is the right-hand side of this inequality is 0, then of course the left-hand side is also 0 for every B. And this means precisely that f of BA, well, f of B star A is 0 for every B. But if B runs over A, then B star also runs over A, and we get this property. Okay, so now let's consider the quotient of A modulo NF. It's rather easy to see that this semi-inner product generates an inner product on the quotient. So the following formula gives us an inner product on the quotient. A modulo NF. It's a simple exercise to show that it is well defined, and it is indeed an inner product. So this quotient becomes an inner product space. Let's denote it by HF0. So this is the quotient of A modulo NF equipped with this inner product. This is an inner product space. In general, the space is not necessarily complete, but its completion is a Hilbert space. Let's denote this Hilbert space by HF. HF is the completion of HF0. And this is Hilbert space. So this is exactly the space where our representation will act. Now let's construct the representation itself. So let's look once again at this formula, which describes NF. So this formula easily implies that NF is not just a subspace of A, it is actually a left ideal. Let's observe that NF is a left ideal in A. This follows from this equality. F of B, no. If A sits in NF, then CA also sits in the same. BCA is, F of BCA is also 0. In general, it is not a right ideal, but we want to construct a representation, not an anti-representation. So it is actually it's convenient that it is actually indeed a left ideal. So the quotient of A modulo NF becomes a left A module in a natural way. A left A module. So we can consider the respective representation. So at this point, by representation, I mean a representation in the pure algebraic sense. A was just an algebra. So let's denote it by pi f0. This is a map from A to the algebra of linear operators on HF0. So this is the respective representation of A. So explicitly it acts by the following formula. It takes an element A to the operator, which takes every element of this space HF0, which is actually a coset of B modulo NF, to AB plus NF. Okay, so far the picture is purely algebraic, but we want to construct a representation of A in the case where A is a C-star algebra, so it must act on a Hilbert space. If A is just a star algebra, then I cannot claim that this operator is bounded, and so it does not necessarily has a natural extension to the completion. But if A is a C-star algebra, then everything is okay, and we get the following result theorem. Suppose that A is a C-star algebra, and F is a positive linear functional on A. then, first of all, the operator pi f0 of A is bounded. And its norm is less than or equal to the norm of A. So this easily implies, this immediately implies that it uniquely extends to a bounded linear operator on the completion on the Hilbert space HF. Pi f0 of A uniquely extends to a bounded linear operator pi f of A acting on HF. So this is true for every A. So we get a map from A to the algebra of bounded operators on HF. And this map turns out to be a star representation, pi f, which acts from A to B of HF, is a star representation of A. Well, of course, the key point here is to prove part 1. So if we prove that this operator is bounded, then of course every bounded operator defined on a normed space uniquely extends to a bounded operator on the completion. And finally, to show that this is indeed a star representation, well, this is just a simple calculation to show that this map preserves the involution. Part 1 is a certain series of estimates based on the C-star axiom, which is not very hard, just about 5 to 6 lines. And in fact, again, this result is true for arbitrary Banach star algebras, but again, the proof is much more involved. So we get a representation, and this representation is called the GNS representation. Pi f is the GNS representation. Associated to F. Okay, now we are one step away from proving another fundamental result in C-star algebra theory, namely the second Gelfand-Deinberg theorem, which implies in particular that every C-star algebra can be faithfully or equivalently can be isometrically represented as an operator algebra on a Hilbert space. Roughly, the idea is very simple. We simply we have to combine all GNS representations corresponding to all states. So to say this more in a more precise, to put it in a more precise form, let's make a short digression to the standard functional analysis and discuss summable families and Hilbert direct sums. Summable families and Hilbert direct sums. So suppose we have a normed space. X is a normed space, or better E. By X we usually denote topological spaces. So suppose that E is a normed space, and suppose we have a family of elements of a family of elements of E. So what we want to do is to give a precise meaning to the following expression. So what does that mean? We know what this means in the case where I is finite, and maybe also in the case where I is a set of natural numbers. But what if I is an arbitrary set? So to answer this question, let's denote by phin of I the set of all finite subsets of I. the set of all finite subsets of I. And let's observe that this is actually a directed set with respect to the usual inclusion. This is a directed poset. Now for every finite subset J of I, let X sub J denote the sum of the elements Xi over J. Of course, this is well defined. So we get a net in X, a net in E indexed by phi null I. And now we come to the following definition. We say that our family is summable our family Xi is summable if this net has a limit. If this net has a limit. And this limit is called the sum of our family. So this is a formal definition. Let's now observe, well, this is actually a rather simple exercise, that the same definition can be given in a more elementary form, which doesn't involve nets at all. An exercise. A family Xi is summable to an element X in E, if and only if it satisfies the following two conditions. First of all, the set, let's denote it by I0, of those indices I for which Xi is not 0 is at most countable. Is at most countable. So, in other words, our family is concentrated on a most countable subset of I. And second, if it is finite, if I0 is finite, then the sum of this family over I0 is just X. And if it is infinite, and if I0 is infinite, so in this case it is strictly countable, it is essentially the set of natural numbers, then for every bijection between natural numbers and I0, that's denoted by phi, for every bijection phi between the natural numbers and I0, the following series x phi of n converges to X. So in other words, we see that essentially summable families are something like unconditionally convergent series. Here it is important that we require this for every bijection. So in particular, if I is exactly the set of natural numbers, then this means that for any bijection from n to itself, the series must converge to the same limit. So in other words, this is precisely the notion of an unconditionally convergent series. So in principle, we see that we don't actually need nets to define summable families, but for technical reasons, the language of nets turns out to be more useful in many situations. Actually, we have already met summable families in the setting where our family consists of non-negative numbers. So suppose that we have a family of non-negative numbers. family of non-negative real numbers. Then a simple exercise is to show that this family is summable. EI is summable if and only if the following supremum is finite. So if we consider all finite subsets of I, for each such subset take the sum over J, over this subset. So J runs over finite subsets of I. So this supremum is finite. This is equivalent to the summability of our family. And moreover, in this case, the sum of this family is just this supremum. I'll not write it again. The same supremum is equal to the sum of this family. So in this case, we use the following standard notation. We simply say that the sum is finite. Okay, so this is the definition of a summable family. Now let's introduce Hilbert direct sums. Suppose that we have a family of Hilbert spaces, Hi, a family of Hilbert spaces. And let's denote by H the set consisting of those elements in their product. So we consider their product taken, so just in the category of vector spaces, such that the following sum is finite. And then a simple exercise is to show that, first of all, H is not just a set. H is a vector subspace in the product. Vector subspace of the product. And moreover, it's a Hilbert space. H is a Hilbert space with respect to the following inner product. If we have two families X and Y satisfying this condition, two square summable families, then the inner product of X and Y is defined to be the sum of the following summable family. The fact that this family is indeed summable follows from the usual Cauchy-Bannikovsky-Schwarz inequality applied to every finite sum of this form. And the completeness is proved in exactly the same way as the completeness of the space little L2. So there's this is rather standard argument. So it's a Hilbert space, and it has a special name. It is denoted like this. So we take the same symbol as for the direct sum, and we put the dot over this symbol in order to distinguish between algebraic direct sums and this construction. And we call it the Hilbert direct sum. The Hilbert direct sum of the family Hi. For example, if all the spaces are one-dimensional, then we just get the usual little L2 space. If Hi is one-dimensional, then this Hilbert direct sum is just little L2 of I. Okay. Let's now extend this construction to representations. Suppose now we have a Banach star algebra. So let A be a Banach star algebra. And suppose we have a family pi I of star representations of A on the Hilbert spaces HI. A family of star representations. And let's observe, so as before we denote by H the Hilbert direct sum of this family. And let's observe that for every element A in A, we can define an operator, let's denote it by pi of A, from H to itself, which acts by the following simple formula. It takes every square summable family X to the following family. So for every I, we apply the operator from the respective representation pi I. Well, why is it well defined? Let's recall that every star representation of a sister algebra has norm 1. So in particular, for every I, the norm of the respective component, of the ith component of this family, can be estimated as follows for every I. And this implies that this family is also square summable. So this is a constant, so we multiply a square summable family by a constant, and again we get a square summable family. So we see that pi of A indeed takes H to itself, takes H to H, and moreover pi of A is bounded. And the norm of pi of A is less than or equal to the norm of A. In particular, pi is bounded. So we get a map pi from A to B of H. And it is very easy to see that this is also a star representation of A. And this representation is called the Hilbert direct sum of the family pi I. And it will be denoted like this. This is the Hilbert direct sum of the family pi I. Okay, so let's now come back to the genius construction. Again, now we assume that A is a C-star algebra. A is a C-star algebra. And let S of A denote the set of all states on A. The set of all states. We define the universal representation, of A, as follows. We denote it by omega A, and this is just the Hilbert direct sum of the GNS representation pi f taken over all states f on A. So we simply take the sum, the Hilbert direct sum of all GNS representations. Unfortunately, I cannot explain why this representation is called universal. It indeed has some universal property, but to explain what this property is, we would have to learn some basics of von Neumann algebra theory. And this is a long story. It would take several lectures. But what is important now is that this representation turns out to be faithful. And this is the famous, the second Gelfand-Nymark theorem. So it states that every C-star algebra has faithful or equivalently isometric star representation. So let's recall from the previous lecture that every injective star homomorphism between C-star algebras is automatically isometric. Oh, not for the previous lecture, but well, maybe 2 or 3 lectures ago we discussed this fact that every injective star homomorphism is isometric. So more exactly, moreover, omega A is faithful. The universal representation is always faithful. Let me just give you a simple, some idea of the proof. The proof is rather simple modulo the results we have already discussed today. Well, indeed, if little a sits in the kernel of the universal representation, then some simple algebraic manipulation imply that for every state f on A, f of A star A squared is 0. But this element is normal. A star A is normal, as A star A squared is also normal. And today we observed that for every normal element, there is a state such that this is equal to the norm of this element. So this implies that this element is 0. A star A squared is 0. Then we take the square root and see that A star A is also 0. And finally, applying the C star axiom, we get that A is also 0. So this is the main idea of the proof. So in some sense, this result is a little bit in the spirit of, for example, of the Whitney theorem in the theory of smooth manifolds, which states that every abstract smooth manifold can be embedded into Rn for if n is big enough. So it is actually a smooth submanifold in Rn, and which is quite useful. So that here the situation is absolutely similar. So we define C-star algebras by a set of axioms, and eventually we see that it is actually can be embedded into B of H, into the algebra of bounded operators on a suitable Hilbert space.
Is it true that square root is unique?
Huh?
Is it true that square root is unique?
The positive square root is unique. For every positive element A, there is a unique positive element B, such that B squared is A. Of course, we can also take minus B, and it is.
Did we prove that it is unique?
No, this was I just said that it is unique and said that it's an exercise. The uniqueness is an exercise, which is a rather simple module of some basic properties of the functional calculus.
Okay.
So basically, we have to use the superposition property of the functional calculus, and you use that if B is a positive element, such that B squared is equal to A, then B is actually exactly the square root of A, which is obtained by the functional calculus. That's the idea. Okay, so the only little disadvantage of this construction is that the Hilbert space where this representation acts is huge. So we take all GNS representations over all states, and the resulting space is very big. Usually it is not separable, even if the algebra A is separable. But on the other hand, if A is separable, then actually we have the following exercise. Suppose that A is a separable C-star algebra. Then, first of all GNS representations act on separable Hilbert spaces. So for every state f on A, the Hilbert space HF is separable. And moreover, if we want to construct a faithful star representation, there is no need to take the direct sum over all states. It turns out that we can always find a state, there is a state f on A, such that the GNS representation pi f is already faithful. So as a result, if A is a separable sister algebra, then it can always be represented as an operator algebra on a separable Hilbert space. Okay. Let's now discuss some basic facts on tensor products of sister algebras. Tensor products of sister algebras. So roughly our goal will be to make the tensor product of two sister algebras into a sister algebra. And here by a tensor product we always mean the tensor product over the complex numbers. The strategy here is as follows. The first step is to take the algebraic tensor product of A and B and to make it into an algebra. And this is absolutely straightforward. The next step is to define an involution on this tensor product. This is also very easy, but it requires a bit of mathematical culture. The next step is to introduce a C-star norm on this tensor product. And this turns out to be rather non-trivial. In fact, we will see that there are at least two natural ways of defining a C-star norm and, on the tensor product, and in a general case, they are not the same. And finally, in general, there is no reason to expect that this tensor product will be complete for this C-star norm, so we must take the completion. And we get a new C-star algebra. This is the strategy. So let's begin with the easy part of this program. We have the following simple proposition. Suppose that A and B are star algebras. Then A tensor B is also a star algebra with respect to the multiplication and involution uniquely determined by the following formulas. So the product of two elementary tensors is again an elementary tensor of the following form. And the involution applied to an elementary tensor AB is just A star tensor B star. Well, why is it true? Well, I'll make no comments on the multiplication. This is just a simple fact about tensor products. So just observe that a bilinear map from A tensor B to itself is a linear map from A tensor B tensor A tensor B, and just interchange two tensor factors in this expression, and you get the multiplication we are looking for. To define an involution, the most convenient way is to use a simple but useful algebraic construction. So idea of proof of part 2. So we observe that for every vector space, if E is a vector space over complex numbers, we can define the so-called conjugate space. Let's denote it by EC. And it is defined as follows. As an additive group, as an abelian group, it is exactly E. But the multiplication by complex scalars is defined as follows. So if x sits in EC and lambda is a complex number, then by definition, lambda x in EC is the same as lambda bar x in E. So formally we get an U vector space where the complex numbers act in a slightly different way. Why is it convenient? It is convenient because when we speak of antilinear maps, like for example an involution on an algebra, we observe that an antilinear map from, say, from E to F is the same as a linear map from A to the conjugate of F. And similar tricks work in the case of bilinear maps, of sesquilinear maps, and so on. So all sesquilinear maps can be reduced to linear maps by using conjugate spaces. Anti-bilinear maps can also be reduced to bilinear maps by using this construction. So this is a rather convenient way of make antilinearity into linearity. So now, if we want to prove part 2, we observe that the involution on A, let's denote it by IA, is a linear map from A to AC. And the same for B. So we may just take now the tensor product of these two maps, IA tensor IB. So it acts to AC tensor BC. And now it's a simple exercise to show that this construction of taking the conjugate space commutes with tensor products. So it is isomorphic natural to A tensor BC. And as a result, we get an antilinear map on A tensor B. And this is exactly the involution we are looking for. Okay. So the next step is to define a C-star norm on the tensor product. Well, just in case, let's give a formal definition. Let's define what a C-star norm is. Suppose that A is a star algebra, and suppose we have a norm on A. We say that this norm is a C-star norm if it almost makes A into C-star algebra. The only difference is that A is not assumed to be complete. So formally, this means that it is first of all it is submultiplicative. It is submultiplicative. It preserves the involution. It preserves the involution, and it satisfies the C-star axiom. For all elements in our algebra. And an algebra, a star algebra A equipped with a C-star norm is called a pre-C-star algebra. Pre-C-star algebra. So the only difference between the pre-C-star algebra and the C-star algebra is that A is not assumed to be complete. But on the other hand, it's a simple observation that the completion of a pre-C-star algebra is a C-star algebra. So what we want to do now is to take the tensor product, the algebraic tensor product of two C-star algebras, A and B. So now we know that it is a star algebra, and to define somehow a C-star norm on this tensor product. The resulting algebra is not necessarily complete, but we can always take the completion and obtain a C-star algebra. Let's start with a simple but important special case of this construction, which corresponds to the situation where one of the algebras A and B is just the algebra of square n by n matrices. Of course, this is a very special case, but we will see soon that it is quite important. Let's introduce some notation. If A is an algebra, let's denote by n of A the algebra of all n by n matrices, n by n matrices with entries in A. In the special case where A is just the field of complex numbers, we'll denote this algebra simply by Mn. So Mn is just Mn of C. And let's observe, it's a simple exercise, that for any algebra A, there is an algebra isomorphism between the tensor product of Mn and A and the algebra Mn of A, of matrices with entries in A, which is uniquely determined on elementary tensors by the following formula. So every elementary tensor in here goes to the matrix with entries alpha ij multiplied by A. And moreover, if A is a star algebra, then this is an isomorphism of star algebras. If A is a star algebra, then this is a star algebra isomorphism. Now I claim that if A is a C-star algebra, then there is a unique C-star norm on this tensor product. A proposition. If A is a C-star algebra, then there is a unique C-star norm on Mn tensor A. And moreover, in this case, there is no need to take the completion because the resulting algebra is already complete. Moreover, Mn tensor A is a C-star algebra with respect to this norm. I'll give you just a construction of this norm, and the uniqueness will be a simple exercise. So idea of proof. Почти, но не совсем. Let me just give you a construction, and then I'll explain what is not immediate about the uniqueness. So the construction is as follows. To construct a C-star norm, we have to apply the Gelfand-Naumburg theorem, the second Gelfand-Naumburg theorem, to A, and take a faithful star representation of A on a Hilbert space H. A faithful star representation. Now, if we take Mn tensor A, we can take the tensor product of this representation by the identity map and get an injective map from here to Mn tensor B of H, which is the same as the algebra of n by n matrices with entries in B of H. But now, let's observe that this algebra, the algebra of n by n matrices with entries in B of H, is nothing but the algebra of bounded linear operators on H to the power n. And this is a C-star algebra. So now to define a C-star norm on this tensor product, we simply restrict it by using this inclusion. And this gives us a C-star norm on this algebra. The completeness is also quite easy. It's a simple exercise to show that this map has closed range. So the range of this map is a closed star subalgebra in B of Hn, so it is complete. And as for the uniqueness, it follows from the following lemma. It follows from the next lemma, which is very close to what you remember, but not exactly. So the lemma is as follows. Lemma exercise. If we have a star algebra, A is a star algebra, and suppose we have two norms two C-star norms on this algebra, C-star norms, such that A is complete with respect to one of them. So suppose that A is complete with respect to one of these norms. Then the norms are the same. So a delicate point here is that when we proved, when we discussed the uniqueness of a C-star norm on a star algebra, the exact statement was as follows. If we have a star algebra, then there is at most one norm which makes it into a C-star algebra. So what does this mean explicitly? This means that if we have two C-star norms such that A is complete with respect to this one and this one, then they are the same. And see, here we require the completeness only with respect to one of them. This is a bit weaker assumption, but nevertheless we see that the norms are the same. So this is not exactly what we know from spectral theory of C-star algebras, but this is very close. So a useful exercise is to prove this result. Okay. By the way, if we don't assume the completeness here, then the result fails. In general, if we have a star algebra, there can be many different C-star norms on this algebra, such that A is not complete with respect to any of them, and the norms are different. And this leads to certain complications in the theory of tensor products of C-star algebras. In particular, it leads to the fact that, in general, there are several natural norms on the algebraic tensor product of two C-star algebras. I see it's time to finish. Okay, so that's all for today. At the next lecture, we complete our discussion of tensor products. So basically, first of all, we extend this construction to a more general setting where we have two different C-star algebras, two arbitrary C-star algebras. This will lead to the so-called minimal C-star tensor product. Then we will briefly discuss another so-called maximal C-star tensor product and discuss the situations where these tensor products are the same. And then eventually I hope we will begin to discuss K-theory. First of all, in a rather simple algebraic setting of arbitrary rings, we define the functor K0. Then we look how to interpret it in the case of C-star algebras, and we discuss some basic properties of this functor.